Hello and welcome to The Space Above Us. Episode 111, Space Shuttle Flight 40, STS-39, Orbital Ballet. Last time, we talked about the flight of Space Shuttle Atlantis on STS-37. Atlantis' main goal was to deploy the second of the Great Observatories, the Compton Gamma Ray Observatory, often shortened to GROW. GROW was already a somewhat unusual payload just because of its considerable mass, but then it decided to put the crew's training to the test by having the high-gain antenna fail to deploy. Jerry Ross and Jay Apt fixed the antenna, GROW was sent on its way, and the EVA crew tested a bunch of techniques for getting around the outside of a space station. One thing I omitted for time was the fact that the crew then used GROW for a bit of rendezvous practice, backing away several kilometers before station keeping and evaluating rendezvous techniques. Originally, there was going to be a dedicated rendezvous practice payload, but there was concern that it could impact GROW at some point down the line. So someone suggested, hey, let's just use GROW itself. The tests were successful, paving the way for the complex rendezvous we'll discuss today. As the crew returned home, GROW began collecting invaluable science data that can only be collected from space. Both STS-37 and the mission before that, STS-35, focused on collecting data in various parts of the electromagnetic spectrum that are blocked by Earth's atmosphere. Both missions focused on some of the most distant and exotic objects known to humanity. Today's mission will also be focusing on multi-spectral imagery taken in multiple parts of the spectrum, but the targets will be a little closer to home. To explain that, let's do a quick refresher on a program that we've discussed before, the Strategic Defense Initiative, aka SDI, aka Star Wars. SDI was a program dedicated to the goal of identifying and destroying ballistic missiles in between when they launched and when they hit something in the United States. It was an incredibly ambitious goal that required a lot of basic research, tricky engineering, and just gobs of money. SDI has run across our path before, with experiments doing stuff like tracking the orbiter with a laser, or Air Force observatories on the ground watching the shuttle while it did stuff. By cross-referencing what they were seeing on their sensors with what the orbiter crew said they had done, the Air Force could learn what certain space-based activities looked like from the ground. By the way, those observations have been noted in the press kit for like every mission since I first mentioned them. I just stopped bringing it up. This sort of basic, what are we even looking for research was critical to achieving the goals of the Strategic Defense Initiative. How are you going to shoot down an enemy spacecraft if you don't even know what they look like? How are you going to know it's maneuvering and thrusting if you can't recognize those activities? Okay, makes sense. But SDI was going to need more than just ground-based observations. It eventually planned to have a small fleet of spacecraft on orbit, keeping an eye out for incoming threats. So SDI also needed to know what this stuff looked like from space. On top of that, they needed a way to not get tripped up by natural phenomena that might look sort of similar to an enemy spacecraft, or might confuse an automated sensor. That's what we'll be diving into today. This mission has a lot going on, so let's just launch and get into orbit, and we'll meet our crew members along with the contents of the payload bay once we get there. The launch was postponed a few times, including a rollback to fix cracks on the external tank door hinge similar to STS-37. It turns out that this wasn't the only issue with the ET doors. I'm getting this from an oral history interview with Mission Commander Mike Coates, so I don't know the exact sequence of events, or if the cracks were discovered as part of this, or if this story impacted the discovery of those cracks on Atlantis, but either way, it's a pretty scary moment. During a long meeting in the build-up to launch, an issue was raised with some paperwork that seemed to indicate that the ET door was not rigged to close properly. The big question was, is this a problem with the door or a problem with the paperwork? The consensus was settling on it being a paperwork issue, with agreement coming from some heavy hitters, like the chief engineer of the shuttle program, as well as the associate administrator for human spaceflight, fellow astronaut Bill Lenore. Coates was on the fence about objecting, since he didn't want to be the only voice going against the consensus, so he was grateful when the Associate Administrator for Safety, Reliability, and Quality Assurance said he was not comfortable. This prompted the Kennedy Space Center director to say that if the safety guy wasn't on board, then he wasn't on board. The time-consuming process of rolling back from the launch pad and demating Discovery would delay the launch, but so be it. When the external tank doors were inspected, they were not properly rigged and may not have closed on orbit, which would have left a huge hole in the thermal protection system. Coates said that the important lesson was to not be afraid to speak up. That's your job. After a trip to the VAB and back, launch day was upon us. April 28, 1991. The countdown proceeded mostly smoothly, but was delayed for 32 minutes when a data recorder started changing modes uncommanded. The crew waited while the recorder was checked out, and at 7:33 a.m., Space Shuttle Discovery lifted off for the 12th time, with an uneventful ride to a 57-degree inclination orbit. Flying this mission was a crew composed of 2 spaceflight vets and 5 rookies. We've got a lot of biographies to get through, so I'll try to keep it brief. Commanding the flight was Mike Coates. We've seen Coates twice now, most recently as the commander of STS-39, deploying the TDRS-D communications relay and saving John Blaha's life. Sort of. If you refer back to the STS-29 episode 98, you can refresh your memory on what I'm talking about. You'll also be reminded that the reason Coates was flying on this mission at all was literally because President George H.W. Bush talked his wife into it, saying that if she permitted him to fly one last time, they were welcome to be guests at the White House again. Diane Coates thought that sounded like a good deal, but no more flights after that, making this Mike Coates' third and final flight. Joining Coates up front was our pilot, Blaine Hammond. Blaine Hammond was born on January 16, 1952 in Georgia, but grew up in St. Louis, Missouri. Hammond attended the U.S. Air Force Academy, picking up a degree in engineering science and mechanics, and later earning a master's in the same subject from the Georgia Institute of Technology. He then joined the Air Force, flying the F-4E fighter jet through the skies of Germany for 3 years. He next bounced around the world a bit as an instructor, flying a variety of aircraft and serving as the program monitor for the High Angle of Attack program, something that I'm sure came in handy with the shuttle. He was selected as an astronaut in 1984, and this is his first of 2 flights. Mission Specialist 1 was Gregory Harbaugh. Gregory Harbaugh was born on April 15, 1956 in Cleveland, Ohio. We can add Harbaugh to our list of astronaut alums of Purdue, since that's where he earned a bachelor's degree in aeronautical and astronautical engineering. He also picked up a master's in physical science a few years later. He joined NASA right out of school, working as a flight controller and mission control for many of the flights in the early history of the shuttle. He was selected as an astronaut in 1987, and this is his first of 4 flights. Sitting in the middle seat was Mission Specialist 2, Don McMonagle. Donald McMonagle was born on May 14, 1952 in Flint, Michigan. McMonagle earned a bachelor's in astronautical engineering and later a master's in mechanical engineering. In between those, he learned how to fly with the Air Force, tooling around in several different aircraft, and of course, attending the Air Force Test Pilot School. Actually, according to his official biography, he not only graduated Test Pilot School, he was the outstanding graduate in his class. So good job, McMonagle. After working at Edwards for a few years as an operations officer for a test squadron, he was selected as an astronaut in 1987, and this is his first of 3 flights. Moving down to the middeck, we find someone we know. Filling the role of Mission Specialist 3, Guy Bluford joins us for a 3rd time. We last saw him flying on STS-61A, floating around inside the pressurized Space Lab module in Challenger's Payload Bay. Bluford actually came pretty close to missing this flight. Several months before the scheduled liftoff, he began experiencing some pain and numbness in his legs. The cause turned out to be a herniated disc in his spine, which would require surgery to fix. He had hoped that the surgery could wait until after his flight, but the condition was painful, made it difficult to stand, and posed the risk of permanent damage. The condition was so debilitating that in an oral history interview, he reveals that just out of frame of the official crew photo was a chair for him to slump into after the picture was taken. Bluford's absence would have been particularly disruptive since he was his team's expert on the payload. But he had no choice but to go for the surgery, and the training staff and the rest of his crew worked around his recovery, cramming in a lot of training once he was well again. Luckily for Bluford, the surgery and recovery all went well, and he was cleared to fly in time for the launch. This is his 3rd of 4 flights. Moving right along, we find Mission Specialist 4, Lacey Veach. Charles Lacey Veach was born on September 18, 1944 in Chicago, Illinois. I think he wins the award for biggest difference between birthtown and hometown, since he considers his hometown to be Honolulu, Hawaii. Slightly different experience in the winter between Chicago and Honolulu. He attended the U.S. Air Force Academy, earning a degree in engineering management before going off to learn how to fly. He served with the Air Force for 14 years, flying several different aircraft, racking up 275 combat missions in the skies of Vietnam, and even flying with the Thunderbirds, performing high-precision maneuvers at air shows. He joined NASA in 1982, serving as an instructor pilot for the Shuttle Training Aircraft. 2 years later, he was selected as an astronaut, and this is his first of 2 flights. And last but certainly not least, Mission Specialist 5, Rick Hibe. Richard Hibe was born on September 21, 1955 in Jamestown, North Dakota. He earned a bachelor's in math and physics and a master's in aerospace engineering, then headed off to NASA. He helped to develop crew procedures and to plan the crew activity timelines. He took a special interest in rendezvous and proximity operations, making him a perfect choice for this flight, which is his first of 3. After successfully arriving on orbit, half of the crew promptly went to bed. The crew had been split into a red team and blue team so that they could work around the clock. On the red team, and at the start of their workday, were the pilot Hammond and mission specialist Veach and Hibe. Heading to bed on the blue team were mission specialists Harbaugh, McMonigal, and Bluford. And as is typical with these split flights, the commander Coates would drift from team to team based on need. While the blue team gets comfy in their bunks and the red team gets used to working in microgravity, let's take a look in the payload bay and see what we've got. Starting way in the back, we find the creatively named Air Force Payload 675, or AFP for short. AFP will be focusing mostly on the don't get confused by natural phenomena side of the Strategic Defense Initiative's problem. There's a lot of weird stuff going on in space in all sorts of different wavelengths. The last thing you want is for your super expensive missile defense system to get all confused because it saw an infrared burble in the upper atmosphere. So AFP 675 will be using a suite of instruments to try to build a baseline for what to expect. The primary instrument was CIRRUS-1A, and you just know that's some sort of tortured acronym. Cryogenic Infrared Radiance Instrumentation for Shuttle. CIRRUS used its specially cooled sensors to examine the dim glow of the atmosphere, as well as the Aurora. Teaching a machine to not be confused by the Aurora seems like a tricky one to me. These bright lights in the sky are caused by charged particles trapped in the Earth's magnetic field being accelerated down into the upper atmosphere. When they hit an atom in the air, they kick one of its electrons up into a higher energy state. When the electron returns back down to its usual energy state, it emits a photon, light. Depending on what gas it hits, different colors are made. For humans, this is harmless and beautiful, creating huge curtains of light that fill the entire night sky. But for a machine in space trying to look for something weird, it's likely to be a good source of false positives. This had the nice side effect for the crew of giving them the unique experience of flying right through the Aurora. In an oral history interview, Mike Coates describes the sensation of floating in a darkened crew cabin while ethereal curtains of light shift around outside. It's something that photos and video just can't capture. Joining CIRRUS-1A were a number of other instruments. The FAR Ultraviolet Cameras experiment, with FAR in all caps but without an acronym explanation, would be looking at air glow, glowing on the surface of the orbiter, and effects caused by the orbiter's thrusters, all in ultraviolet. Air glow is sort of like a much less bright version of the Aurora that happens all the time. With a low-light camera in space at night, you can see the atmosphere like it's a thin shell around the Earth. And as we've discussed previously, due to the effects of atomic oxygen, some surfaces on the orbiter can glow, which can be disruptive to sensitive instruments. The Uniformly Redundant Array is a boring name for a neat instrument looking for X-rays from stars, while carefully filtering out false positives from other energetic particles. The Horizon Ultraviolet program would be doing pretty much what it sounded like, characterizing the UV response of the Earth's horizon. And lastly, the Quadrupole Ion Neutral Mass Spectrometer. In addition to being a mouthful to say, it was an instrument for measuring any contamination in the orbiter's payload bay, so folks would know when it was safe to activate CIRRUS. For the most part, AFP ran great, and in the end the experiment was deemed a success, but it did hit a couple of hiccups along the way. First, the primary instrument, CIRRUS, required special cryogenic cooling in order to operate. Unfortunately, it was churning through its cryogenic supply faster than expected. This was problematic since CIRRUS could not operate at the same time as the other mission payloads. To prevent contamination from the orbiter's thrusters, it could only be operated while in a gravity gradient stabilized attitude. To compensate, it was given priority early on in the mission, and the other payloads we'll be discussing were rescheduled for slightly later. The second hiccup was a little more dramatic. The data recorder failed for the Horizon Ultraviolet program and the instrument that detected if it was safe to run Cirrus, the Quadrupole retroencabulator or whatever. Not to be deterred, the ground came up with a workaround that the astronauts then executed. This is dryly conveyed in the official mission report as, quote, "The crew performed an in-flight maintenance procedure that was developed by ground personnel and regained the ability to route data from the HUP and QI-NMS experiments to the ground personnel using the KU band antenna." What that leaves out is that the crew literally opened part of the orbiter wall, cut some cables, and spliced them together in order to connect the payload directly to the KU band antenna. It's like something out of a sci-fi movie, and if you told me they did this, I would not have believed you. Next up, in the middle of the payload bay, was the main payload for the Strategic Defense Initiative, the Infrared Background Signature Survey, or IBSS. Future NASA Administrator Mike Griffin was pretty high up in the SDI organization, and when he met STS-39 Commander Mike Coates, his first words were, "There's a $25 billion program riding on the data you get, so don't screw it up. No pressure now." The task of IBSS was to gather multi-spectral data on what a maneuvering spacecraft looks like from space, something that had never been done before. 3 of those spacecraft would be small sub-satellites that we'll talk about in a bit, but the primary target would be the orbiter itself. But in order to observe the orbiter maneuvering, IBSS was going to need a way to fly on its own. And it turns out NASA had just the thing to make this happen. Our old friend, the Shuttle Pallet Satellite, or SPAS. We last saw SPAS way back on STS-7 in 1983. After taking some snappy photos of Space Shuttle Challenger and being plucked out of orbit by mission specialist Sally Ride, SPAS had returned to Earth, waiting for its next chance to fly. I'm not sure where it's been for the last 8 years, but I'm happy to see it back. Since it's flying for a second time, it's now called SPAS-2. I'll be using the terms IBSS and SPAS sort of interchangeably, but if you want to be precise, IBSS is an experiment flying on the SPAS platform. Like Cirrus, IBSS carried a sophisticated cryogenically cooled infrared sensor, and also an ultraviolet sensor and some low-light television cameras. The images captured by IBSS could be viewed by the shuttle crew and by the ground, helping to guide operations. On Flight Day 2, SPAS was unberthed but remained on the end of the robot arm while Cirrus finished its observations. On Flight Day 3, the 2-ton platform was released and Discovery carefully backed away. This kicked off 38 hours of the most complex series of rendezvous and proximity operations maneuvers in the entire shuttle program. At least according to longtime Rendezvous mission controller and author of an excellent history of Space Shuttle Rendezvous, Dr. John L. Goodman. And based on what I've seen, I'm inclined to agree. SPAS had the easy half of the equation for these maneuvers. Its job was to sit in one place, relatively speaking, and just keep its cameras pointed in the right direction, while Discovery executed dozens of carefully coordinated maneuvers. Just as a quick jargon reminder, in Rendezvous you typically build a reference frame with your target placed at the center. So in our reference frame, wherever SPAS-2 is, that's the origin. The part of this frame that we care about today is called the V-bar, which is just a line along the direction of travel, the velocity, hence V-bar. If you're ahead of SPAS in its orbit, you're on its positive V-bar. If you're trailing behind it, you're on its negative V-bar. The entire sequence that we'll be discussing today essentially just involves moving around on SPAS-2's negative V-bar, with a few excursions off of it for specific tests. At the risk of belaboring the point, imagine that you're on a highway and there's a truck ahead of you. You're on the truck's negative V-bar. If you were to slow your car down a little, you'd move backwards relative to the truck. If you were to speed up a little, you'd move forwards relative to the truck. So while both vehicles are still cruising down the highway, you're moving forward and backward in relation to the truck. Replace the truck with SPAS and yourself with Discovery, and you've kind of got the right idea. The first maneuver was straightforward enough. A separation burn of about 2/3 of a meter a second of delta V. This maneuver actually pushed Discovery along the direction of travel, the plus V-bar, which raised its orbit, causing the orbiter to drift up, and then thanks to the counterintuitive dynamics of orbit, it drifted down the negative v-bar, falling back on the highway. This is because in a slightly higher orbit, Discovery was slightly slower than SPAS. We're already getting into the weeds here, so I'll restate all that simply as Discovery moved about 10 kilometers behind SPAS. Obviously, SPAS was watching all this and gathering data on thruster firing, but that was just the start. What came next was a series of maneuvers that the folks at work would call sporty. The crew called it the Malarkey Milkshake, after the designer of the maneuver, John Malarkey. First, Discovery oriented itself 90 degrees to the direction of travel. So if it's flying east, Discovery is now pointing north, out of the orbital plane. Then, it used one ohms engine to execute a 5 meter per second burn, which is pretty big. As soon as that was done, it used the RCS thrusters to quickly flip around 180 degrees, so now its nose is facing south. Only 5 minutes after that first big burn, it again used a single ohms engine to null that cross-track velocity. Now it's about 1,500 meters out of plane, and it would then slowly return to the original position by using these smaller RCS thrusters. The whole excursion spread about 12 meters a second of delta V across 4 maneuvers, executed in only 27 minutes, with 2 big burns and a 180-degree flip only 5 minutes apart. That's sporty. To return to our highway metaphor from earlier, SPAS is a truck 10 kilometers ahead on the highway, and Discovery is quickly changing lanes so SPAS can watch and see what that looks like. Except in this case, the highway would have to be 1,500 meters across, which is a pretty wide highway. The Malarkey Milkshake was repeated 2 more times at this 10-kilometer far-field location. Discovery also performed a similar cross-track maneuver using the RCS thrusters to see if they looked any different. All of these maneuvers provided lots of juicy data for IBSS to chew on, as well as producing some pretty impressive video footage. Once it was done with the far field, it was time for Discovery to transition to the near field, a little more than 2 kilometers behind IBSS/SPAS-2. That name just rolls off the tongue. But first, we actually have a whole other payload to introduce on this increasingly complicated mission. The Chemical Release Observation, or CRO experiment, consisted of 3 mini spacecraft that would be ejected one at a time out of Discovery's payload bay. Before heading to the near-field station, CRO-C was popped out of the payload bay in a way that would cause it to drift even further back in orbit. Imagine a cylinder about the size of a mini-fridge with a big satellite dish on front of it so it could reflect radar, and you've got a pretty decent mental picture. When CRO-C was in the right lighting conditions, and when IBSS, Discovery, and a ground station at Vandenberg Air Force Base could all see it, the sub-satellite began spraying its chemical payload into space. In the case of CRO-C, that was 15 pounds of nitrogen tetroxide, a common rocket fuel. This created a big cloud that sensors both on the ground and on orbit could inspect. This would not only give SDI a clue as to what a mystery object might be, but it could also be used to get around sneaky countermeasures. For example, maybe a nuclear warhead would emit a big cloud of gas to hide the warhead's exact position. The CRO experiment hoped to prevent that. We'll leave CRO-C to do its thing and follow Discovery along to the near-field station considerably closer to SPAS, only about 2 kilometers back. Once there, it performed 2 more iterations of the Malarkey Milkshake. Finally, it moved 13 kilometers back from there so that it could perform a standard rendezvous approach. On the way, CRO-B was ejected, later emitting 52 pounds of unsymmetrical dimethylhydrazine, another rocket propellant. As the orbiter approached SPAS, the crew started experiencing some issues with the rendezvous radar. The data started to get noisy, or even dropping out entirely. One of the backup methods involved using angle data from the cameras in the payload bay, but then those started giving the crew trouble. Mission Commander Coates recalled how in training they never actually completed a full end-to-end simulation. Halfway through, the sim would crash, with the visual, the view out the window, going blank. Really, that wasn't that big of a deal. They just switched to the second half of the rendezvous. But now, flying a few hundred miles above the Earth, it prompted someone on the crew to quip that he hoped that they didn't lose the visual this time. The ratty data caused the crew to be a little more conservative with their maneuvers, which actually led to a pretty smooth and efficient rendezvous. So 38 hours after it dropped SPAS off, Discovery moved in and used the RMS to snag the free-flying experiment. A few hours later, the Crow experiment was completed with the deployment of Crow A containing 60 pounds of monomethylhydrazine. The IBSS and Crow parts of the mission were complete. Of course, all of this was just a top-level summary, and even then that was pretty complicated. In the real world, things don't always behave like they do in the simulations. Estimates need to be made for drag, for solar radiation pressure, for unmodeled forces caused by the always active orbiter doing stuff like venting. Maneuvers don't always happen exactly on time, and sometimes they happen outside of communications range, so the ground doesn't even get all the thruster data. One maneuver was calculated using an overly large estimate for these vent forces, and then was executed 2 minutes late, leading to some large radial dispersions that had to quickly be cleaned up. SPAS was so bright in the camera that the sensor bloomed, making it difficult to read angle markers. These are all the little problems that can't be precisely anticipated, but can be solved on the fly by a well-trained crew and dedicated ground support. And then they get rolled into training for the next mission. This is how progress gets made. During all of this, life continued aboard the orbiter. The red team and blue team swapped places, one sleeping in their bunks on the middeck while the others did their work. Lithium hydroxide canisters were swapped to keep the carbon dioxide levels down, meals were made in the galley, and the crew worked out using the special zero-gravity treadmill. Well, until Flight Day 6, when pilot Blaine Hammond was running on it, and the darn thing broke. The mission report sort of dramatically describes this as, quote, "The pilot reported hearing a snap, after which the treadmill resistance increased to infinity." To infinity! Oh well. One of the crew members later said they weren't too bothered by no longer having to strap into the contraption every day. Believe it or not, we're still not quite done with the payload bay. Mounted across the center and a number of large canisters was the Critical Ionization Velocity, or CIV experiment. This was sort of like the Chemical Release Observation experiment, but rather than releasing gases from sub-satellites hundreds of miles away, it was just released right in the payload bay. I'm not sure why, but I would guess it's because the chemicals released by Crow were nasty rocket propellants, while the chemicals released by CIV were a lot more benign. Instead of hypergolic fuels, it was xenon, neon, carbon dioxide, and nitrous oxide. As the name sort of hints, the goal here was to see if otherwise neutral gases would become ionized by flying through the Earth's magnetic field at orbital velocity. That might cause them to emit light and make them easier to detect. All four gases were actually released earlier in the mission, so SPAS could observe them, but I didn't want to overcomplicate the already complex rendezvous sequence. The last gas, nitrous oxide, had a special treat for the crew. It was actually visible, leading to some pretty neat photos. And lastly, something was ejected from a multi-purpose experiment canister mounted on the side of the payload bay. What it was, we have no idea, because this was the only part of the mission that was classified. Maybe the Department of Defense just wanted to remind us that this was, in fact, a DoD mission. Officially, only Mission Specialist Guy Bluford and Commander Mike Coates knew what was in the canister, but this was actually sort of a point of contention. The Air Force didn't want anyone else on the crew to know anything about this, but as Coates puts it, quote, "Well, when everybody's crowded together on the flight deck and they see something go poof, they're going to notice. I can't tell them to close their eyes. It doesn't work that way up there." Whatever the mystery object was, it was successfully deployed on Flight Day 8, and no one on the crew spilled the beans. One real quick note that I thought was sort of strange. On this flight, Discovery had been upgraded to use some new general-purpose computers. This didn't really impact anything on this flight, but with more memory and more reliability, it opened the door to improved software down the road. For now, though, it was enough to just check that the new computers were running and had no issues. The strange part is that the paragraph in the press kit talking about this states, quote, "On STS-39, Discovery's avionics system will feature the first set of 5 upgraded general-purpose computers, plus a spare, to fly aboard the shuttle." That caught my attention, since the STS-37 press kit said, quote, "On STS-37, Atlantis' avionics system will feature the first set of 5 upgraded general-purpose computers, plus a spare, to fly aboard the shuttle." So which one was first? Maybe I caught the press kit authors engaging in a little copy-pasting, but who knows. With their incredibly complex mission complete, it was time for the crew to come home. The original plan was to land at Edwards, and in fact the crew's families and some VIPs were waiting for them there. But mere minutes before the deorbit burn, literally something like 5 minutes, the decision was made to land in Florida instead. No problem for the well-trained pilot crew. They quickly updated the computer, which ensured that they would take the proper entry trajectory. This particular trajectory was a little unusual, in a good way. Discovery would fly over much of the United States, starting in the northwest, passing over the Great Plains, and landing in Florida. Because of the specifics of this entry, much of it was in a long left bank, so the left side of the vehicle was pointed down. As luck would have it, it was a clear day over America's heartland. Commander Coates found himself as the only crew member with a sizable window that looked out over this incredible view, so he did his best to convey it to everyone else over the intercom. He could see the Rocky Mountains, individual yellow school buses, contrails from passenger jets 170,000 feet below them, all while flying at 20 times the speed of sound. But at one point, an unattributed crew member, perhaps someone down on the middeck with only the lockers to look at, called out, "Oh, shut up!" After 8 days, 7 hours, 22 minutes, and 21 seconds, Discovery touched down at the shuttle landing facility at the Kennedy Space Center, and STS-39 was in the books. Mike Griffin, who had stressed the importance of the data this mission was to gather, said that they got more data than they ever could have dreamed of. The mission was a complete success. Oh, and one last little epilogue. Mike Coates got to fly for a third time on this flight thanks to President Bush's cajoling. Well, Mr. Bush kept up his end of the bargain, and Coates and his wife were indeed invited back to the White House, where they joined the president in a game of horseshoes in the Rose Garden. Next time, Columbia is back with another Space Lab mission. In the past, we've launched chimps, we've launched rats, and we've even launched a swarm of bees. On this flight, we'll find out what happens when you send thousands of jellyfish into low Earth orbit. Ad Astra. Catch you on the next pass.